Welcome to The Explainer. Today we're taking a closer look at the absolute unsung hero of our planet, Earth's atmosphere. I mean, just think about our neighbors for a second. You've got Mars with an atmosphere so thin and unbelievably cold that liquid water doesn't stand a chance. And then there's Venus, which is basically a 450-degree pressure cooker. But Earth? We happen to exist in this razor-thin, absolutely perfect zone of chemical composition and physical structure. It is literally the only thing standing between a living, breathing, vibrant world and just another sterile rock floating in space. So let's dive right in. You know that famous blue marble photograph? The one the Apollo 17 crew took back in 1972 from, 45,000 kilometers away? If you look closely at the very edge of the planet in that picture, you see this faint, luminous blue haze. That's it. That's our entire atmosphere. And it really hits home just how incredibly delicate the whole system is. To put it into perspective, it's a layer so thin compared to Earth's massive radius that if you shrunk our planet down to the size of a standard classroom globe, the entire atmosphere would fit inside the thickness of a single coat of lacquer painted on the outside. Seriously, it is an incredibly fragile planetary shield, just this incredibly thin envelope of gas hugged against the Earth by gravity. All right, so what's actually in this ultra-thin shield of ours? If you take a deep breath of dry air at sea level, you're overwhelmingly breathing in nitrogen, oxygen, and just a tiny dash of argon. Combine those three and you've got over 99.9% of the air around us. They are the absolute heavyweights, and their levels, they stay pretty much rock-solid constant over human timescales. But here's the really wild part. Despite making up almost the entire atmosphere, these major gases are virtually transparent to the Earth's outgoing heat, which means they actually aren't the ones pulling the levers on our global climate, not at all. If we want to find the true climate controllers, we have to look at that tiny leftover fraction. 0.042%. That's it. That infinitesimally small number represents the total atmospheric concentration of carbon dioxide as of 2024. And this brings us to a really fascinating concept called the trace gas paradox. How on earth can a fraction of a percent control the thermal fate of the entire planet? Well, it all comes down to physics. Carbon dioxide is a greenhouse gas. So it lets incoming visible sunlight pass right through it, kind of like the glass roof of a greenhouse. But it absorbs the outgoing infrared radiation, the heat, basically, that the Earth's surface naturally tries to radiate back out into the freezing void of space. It essentially acts like a thermal blanket, trapping that energy inside our little coat of lacquer. Now, when we look back at the historical data, pre-industrial CO2 levels were sitting at around 280 parts per million. Today, we've officially breached 420 parts per million. And if we look at ice core records, that current concentration is the highest it has been in at least 800,000 years. Not only that, but it's climbing by roughly 2 to 3 parts per million every single year. The data clearly shows that human activities, specifically things like burning fossil fuels and widespread deforestation, are the primary drivers shifting this extremely delicate balance. And the result is a significantly enhanced greenhouse effect. It's just a powerful reminder of how hypersensitive our atmospheric chemistry really is. But hey, while CO2 definitely gets most of the spotlight, it is absolutely not flying solo here. Take water vapor, for example. It's actually the most abundant greenhouse gas out there, and it acts as this massive amplifying feedback loop. Think about it. Warmer air holds more vapor, which in turn traps even more heat, which then warms the air even further. Then you've got methane. Its concentration is incredibly small, but its global warming potential is roughly 80 times stronger than CO2 over a 20-year time frame. No joke. Throw in nitrous oxide and synthetic CFCs, which, by the way, also destroy the ozone layer, and you've got this highly potent interactive cocktail of trace gases managing the planet's heat. Okay, so let's actually take a vertical journey. Because the atmosphere isn't just one big uniform soup of gas, it's beautifully structured into very distinct layers. We start right down here at the surface, in the troposphere, which reaches up to about 12 kilometers high. This is our neighborhood. It holds 80% of all the atmospheric mass, and pretty much all of the moisture that drives our daily weather. And if you've ever flown in a plane or hiked up a really tall mountain, you've experienced what's called the normal lapse rate. Basically, the temperature steadily drops about 6.5 degrees Celsius for every single kilometer you go up. Makes perfect sense, right? But right as we hit the absolute ceiling of the troposphere, a boundary line we call the tropopause, something bizarre happens. The temperature just completely stops dropping. In fact, if you had a thermometer strapped to a weather balloon passing through this boundary, you'd watch the temperature suddenly start going up as it continued its climb into the freezing sky. This reversing thermometer effect is actually what defines the boundaries of our atmospheric layers. So the big question is, why on earth does the temperature suddenly start rising in a thin, freezing environment so high above the ground? Well, the answer to that mystery lies right in the stratosphere. Up here, the famous ozone layer is hard at work absorbing high-energy ultraviolet radiation from the sun, specifically those really nasty UVB and UVC rays. And it actually converts that lethal radiation directly into heat. Because the air is actively getting warmer the higher you climb, it creates what we call a temperature inversion. You've got warmer air sitting neatly on top of cooler air. And because of that, the stratosphere is unbelievably stable. There is almost zero vertical mixing going on. It's essentially a stagnant pond of air. But the downside to that stability is that when things like volcanic ash or ozone-depleting CFCs get injected up there, they can just get stuck, floating around for months or even years. And actually, since we're talking about ozone, we really need to clear up a very common source of confusion: the difference between the good ozone up high and the bad ozone down low. Stratospheric ozone, the stuff we just talked about, is an utterly irreplaceable shield. It absorbs over 97% of the sun's UVB radiation. It literally stops widespread DNA damage, skin cancer, and the total destruction of plant life. It's a lifesaver. But tropospheric ozone, the ozone that forms right down here at ground level where we're breathing, that is a completely different story. Down here, it's a really harmful pollutant. It's actually a primary ingredient in photochemical smog that severely damages our lungs. Same exact molecule, wildly different impact depending entirely on its altitude.
Let's keep climbing. Past the ozone layer, spanning from 50 to 80 kilometers up, we enter the mesosphere. Because we finally moved above that heat-generating ozone, the temperature gradient flips yet again, and the temperature absolutely plummets. In fact, right at the top of this layer, the mesopause, we hit the absolute coldest temperatures in the entire atmosphere. We're talking a bone-chilling minus 90 degrees Celsius, sometimes even colder. Now, the mesosphere is a bit of a mysterious no-man's land. It's too high for weather balloons or aircraft to reach, but it's too low for satellites to maintain an orbit. Even so, it is absolutely vital. This freezing, super sparse layer is exactly where the vast majority of incoming meteors hit the friction they need to completely burn up before they can strike the Earth. Finally, we punch through the 80-kilometer mark, and we are officially at the very edge of space, the thermosphere. And guess what? The thermometer reverses one last time. Temperatures up here literally skyrocket, reaching anywhere from a few hundred to well over 2,000 degrees Celsius. This intense heat is caused by super sparse oxygen and nitrogen molecules absorbing incredibly high-energy solar UV and X-ray photons. But here's the catch. The air up here is so unimaginably thin that the concept of temperature really just means the raw kinetic energy of a few fast-moving molecules. If you were somehow just floating out there in the thermosphere, you wouldn't feel 2,000 degrees of burning heat. You'd actually freeze to death. The gas density is so incredibly low that there's practically zero heat transfer to your body. It's bizarre, right? By the way, this electrifying layer is also where we get those stunning auroras. And it's the very layer where the International Space Station is orbiting our planet right now. So, stepping back and looking at the whole shebang, you can really see how all these distinct stacked layers and tiny trace gases work together as one giant, brilliantly engineered planetary thermostat. First off, you've got the natural greenhouse effect. Without it, Earth's average global temperature would be a devastatingly cold minus 18 degrees Celsius. But our natural greenhouse gases bump that up by a massive 33 degrees, giving us a very comfortable global average of 15 degrees Celsius. Second, you have pressure regulation. The sheer weight of all that gas stacked up gives us the exact atmospheric pressure required to keep water in a liquid state on the surface, and lets our lungs actually process oxygen. And third, temperature moderation. The atmosphere's heat capacity acts as a massive thermal buffer. I mean, just look at our moon. It has no atmosphere, and it swings wildly from 127 degrees Celsius during the day to a freezing minus 173 degrees at night. Our atmosphere completely prevents those violent lunar-like swings. We've seen just how massive, complex, and brilliantly balanced this perfectly layered atmospheric machine truly is. It perfectly regulates surface pressure, it acts as a literal shield against meteors and lethal radiation, and it keeps our global temperatures incredibly stable. But we've also learned about the trace gas paradox. We know that a tiny fraction of a percent of certain gases literally holds the thermal reins of this entire massive system. So the big question we're left with, the one we really have to ask ourselves, is this: how do our own tiny trace gas emissions threaten this incredibly delicate balance? As we continue to tweak the precise chemical makeup of that unbelievably thin coat of lacquer, what does that actually mean for the future of our planetary shield?
Something to chew on the next time you step outside and take a deep breath of fresh air. Thanks so much for joining me for this explainer. Keep learning, keep questioning, and I'll catch you in the next one.